Hello and welcome. Today's going to be a thrilling class where we're going to do many things. We're going to learn how to manipulate four tensors. These are tensors which live in space-time. We're going to learn about the tensorial equivalent, or the tensorial generalization of both velocity and acceleration. We're going to have some introduction to relativistic mechanics, where we do mechanics from a tensorial perspective. We're going to tensorialize momentum and state the hypothesis of conservation of four momentum. We'll develop some identities for four momentum, with this tensorial version of energy, also called the energy momentum tensor. And if we have time, we'll consider relativistic billiards, relativistic collisions, not with relativistic billiard balls, but with relativistic particles. So let's launch with 21, about manipulating four tensors. Yep. Now, we spoke about tensors in the general setting, arbitrary n-dimensional spaces, but the space of interest for us is going to be space-time. And when we speak of tensors, as always, a tensor is a tensor if it transforms as a tensor. A Lorentz tensor is a Lorentz tensor if it transforms as a Lorentz tensor under the Lorentz transformations. Now we'll be speaking of these so-called qualified tensors, tensors in space-time, which are also called four tensors, but often I'll just drop the qualification and speak of tensors, but we're always speaking about four tensors, tensors which live in space-time and which transform as tensors according to the Lorentz transformations. Remember also that the position coordinate in space-time, x0, 1, 2, 3, formerly called CT, X, Y, and Z, which in the superscript notation, Greek index can go through 0, 1, 2, 3. This will be a position vector in space-time. And we saw that for tensors that infinitesimal displacements were the blueprint, were the archetype for the rank 1 index, contravariant, upstairs index. The rank 1 contravariant tensor, this tensorial version of a vector, was an archetypal rank 1 tensor. When we restrict ourselves to linear coordinate transformations, the position coordinates transform the same way that coordinate differentials transform. Question, how do coordinate differences transform? Coordinates transform, well, that is the Lorentz transformations. So let me just rewrite the Lorentz transformations in replacing Tx, Y, Z with the x superscripts. When you do that, you'll get equations 110. The time coordinate, again, whether I prime the coordinate or the index is immaterial, and I'll switch between the two. Our gamma factor, our position, our time, our position, x1. So this is our first Lorentz transformation written in the tensorial language. X1 prime, gamma into x1, the x0 on C. The y and the z, the x2 prime and the x3 prime are unchanged, and we have the usual pair of inertial reference frames in standard configuration with respect to one another. We've seen that enough times that I don't need to draw it. As always, you could apply a V reversal to write down the corresponding inverse transformations. You could do the V reversal. Remember that that's a two-step process. Step 1, replace V with minus V. Step 2, interchange primed and unprimed quantities. This will give you, if you start with a valid relativistic transformation such as this, the V reversal will give you another valid relativistic transformation. In this case, applying a V reversal to these objects will give you the inverse Lorentz transformations, which I write down. Now, we know that a tensor is a tensor if it transforms as a tensor. If I was to have an arbitrary rank, arbitrary rank mixed tensor, I'm just using random Greek indices, it will transform as a tensor. Now again, we need to remember nothing. On the left-hand side, I have the indices. On the right-hand side, I have the indices. Depending on which way I want to transform, I'll either prime all the left or all the right. Let me just randomly choose to prime all the indices on the right. This mu prime must be summed over to be gotten rid of. So the mu prime with the Einstein summation convention is now gone, replaced with a mu upstairs index. Again, Einstein summation convention of repeated upstairs and downstairs index is summed over. Nu prime, similar logic, has to go. with nu being a free index. Notice that here we have these p's, which by definition, the p mu prime, for example, by definition, will be dx mu dx nu prime. And I'll just remind you that an upstairs index in the denominator becomes a downstairs index. This is the derivatives of the old coordinates with respect to the new, and if you flick the prime and the unprimed, you'll get the derivatives of the new with respect to the old coordinates. So here we have the derivatives of the old coordinates with respect to the new, if we call the old unprimed and the new primed. And this, by the way, is how the upstairs indices transform. Downstairs indices transform differently. Instead of involving the derivatives of the new with respect to the old coordinates, we have the opposite. I want to get rid of that theta prime. I need a theta subscript as a free index. There we have new coordinates differentiated with respect to old. And the final index, which comes in here, I'll just write down here, we need to sum over the phi prime and have a phi as a free index. So this is how an arbitrary mixed rank tensor transforms. But in order to be able to transform an arbitrary mixed rank tensor, I need to know what these p's are. But these p's I can read off directly from the Lorentz transformations. Yep. The p's I can read off directly from the Lorentz transformations. The p's that go one way, or the p's that go the other way of interchange primed and unprimed quantities. So the question, if I can work out these p's by staring at the Lorentz transformations, I'll be able to transform any mixed rank Lorentz tensor, arbitrary mixed rank Lorentz tensor. So how do I read off the p's? Well, let me give you a few and I'll leave the rest as an exercise. If, for example, I wanted to know what p naught prime naught was, yep, this will be dx naught prime superscript, dx naught superscript, yep, superscript in the denominator is a subscript. And what is dx naught prime dx naught? Well, I need to differentiate this object with respect to this. And what I'll get will be the coefficient, gamma. So this gives me one of my p's. As a second example, suppose that I wanted to work out p naught prime 1, just for the sake of argument. P naught prime 1. Again, by definition, that would be dx naught prime dx 1. I want to differentiate this with respect to the x1, and I'm going to pull out the coefficient, which is minus gamma v on c. And so on, yep. So using this procedure, I can look at the Lorentz transformations and read off an arbitrary p. Remember also that since the coordinates are the archetypal rank 1 tensors, if I was to rub off the x's, these x's are the blueprints. This is the blueprint for an archetypal rank 1 4 tensor. Yep. So if you ask me the question, if I have an archetypal rank 1 contravariant tensor, how does it transform? Well, the answer is exactly the same way as the x's. This is how the x's transform. And if I replace each x with an a, I will have the transformation law for an arbitrary rank 1 contravariant tensor. Yes, we're taking this idea of a blueprint seriously. Tensors are tensors if they transform as tensors, and the rank 1 arbitrary contravariant 4 tensor transforms in exactly the same way as the position coordinates, in exactly the same way as the Lorentz transformations. So the concepts of tensors are, of course, interesting and difficult, but if you stare at it enough, it becomes natural. And it's not just the language of relativity that is most naturally couched in terms of tensors, but there's a vast variety of other fields of physics, such as quantum mechanics, quantum field theory, string theory, particle physics, fluid mechanics, continual mechanics, general relativity, and the list goes on. I now want to introduce tensorial versions of velocity and acceleration. The tensorial version of velocity will be denoted by a capital V or a capital U, and the tensorial version of acceleration will be denoted by a capital A. So for velocity, and for acceleration. When I have the preface, the word for, I mean these objects are tensors. Velocity is not a tensor, acceleration is not a tensor. We seek a tensorial description of the physical world. We seek tensor equations. And part of the way towards getting tensor equations is to have tensorial quantities in physics. And since we're talking about relativistic mechanics here, we want to tensorialize our various quantities in physics. And here, we want to tensorialize the concepts of velocity and acceleration. Now, let's consider two events in space-time. P and Q, and suppose that those two events could, in principle, be connected by some material particle. Now, we've introduced this idea of an infinitesimal squared interval, and we know that if this object is greater than naught, then we speak of the separation between these events in space, in space-time as being time-like. This corresponds to the pair of particles being able to be connected. A material particle could travel from Q to P. Now, we've argued that the delta S squared, or its infinitesimal version, if these events are infinitesimally close, this will be ds squared. We argued that this ds squared is an object upon which all inertial observers agree. There's two events. They can be coordinatized in any inertial frame, but those two events will have a coordinate difference, which in non-tensor language will be dx dy, dz. We could tensorialize this if we wanted to. But the point is, this object here, we argued, was an invariant, a rank 0 tensor, to use our current language. So this is a rank 0 tensor. This is an object upon which all inertial observers agree. So let me now divide through by c squared. If I divide through by c squared, this c squared is gone. This is divided by c squared. The negative is at the front of the whole fraction. So this object here is going to be something upon which all inertial observers agree. It's an absolute. It's a rank 0 tensor. It's a Lorentz scalar. And I'm going to give this a name, d tau squared. Now, I claim that I'm going to call this tau the proper time, and I need to justify this statement. And I'm going to justify it two different ways. Remember that the proper value of any quantity is the quantity that that value takes in an inertial frame in which it's at rest. So the proper value of the length of this ruler is the length that this ruler has when it's at rest. The proper value of the mass of this chalk is the mass that this chalk has when it's at rest, or in a frame in which it's instantaneously at rest. The proper time, for me, as I walk around the room, is going to be the time that I read on my wristwatch, because this wristwatch, even if I'm in an accelerating frame, this wristwatch is always at rest relative to me, right? Because it's attached to my hand, and I'm not moving my hand relative to myself. So the time that this wristwatch reads would be my proper time, the proper time, and it's a natural way to parameterize my motion through space and time. Yep. But I still need to justify calling this thing the proper time, and I want to justify it, well, it's really just one way in two slightly different guises. If we imagine two events, here's two events, two clicks, and so I'm the material particle, and there's two clicks, right, which are infinitesimally close together. Now those might be displaced in space and time as far as you're concerned, but as far as I'm concerned, those two clicks were exactly the same coordinate, right? Those two successive clicks were exactly the same coordinate for me in my frame. And since this is an absolute, every inertial observer will agree on the value of this. Let me calculate it. I can calculate it in any frame. Very important logic, which we'll use again and again. This is an absolute because this is an absolute and this is an absolute. Hence, their quotient's an absolute. This is an absolute. Therefore, this value will be the same when calculated in any frame. Let's calculate it in the rest frame. So if we go to the rest frame, that frame of reference that's rigidly attached to the particle, pair of events, and for those pair of events, dx, dy, and dz will all be naught. So in the rest frame, d tau squared equals dt squared. I want to reject the negative sign for reasons you might think about. In the rest frame, this is the time that's elapsed. So since it is the time that's elapsed in the rest frame, I can call it the proper time. A second way to derive exactly the same result, a second albeit related way to derive exactly the same result, is to look at this expression and to divide through by dt squared. So I'm looking at this expression here, dividing through by dt squared. So I have d tau squared, dt squared, tau and t. Divided through by dt squared, I get 1 minus. Now there's the c squared. If I divide dx squared plus dy squared plus dz squared divided by dt squared, I'll get nothing more than the speed squared. And think of dx, dy and dz as infinite, as small but not infinitesimal. Then you take the limit. Dx squared plus dy squared plus dz squared divided by dt squared. We've divided this and this by dt squared, gives us speed squared, which I call u. If I now take the square root of this expression and reciprocate, just to repeat, if I square root this expression and reciprocate, this will be dt d tau. This thing will become 1 over the square root of, which is just the gamma factor. Hence, dt equals gamma d tau. But this is time dilation. Moving clocks run slow by a factor of gamma. Yep. We've just very swiftly derived time dilation. The time elapsed in the frame attached to the particle needs to be multiplied by the gamma factor to get the time elapsed according to some arbitrary inertial frame. This is a second way of demonstrating that d tau is the proper time. Again, I emphasize that proper time is a very, very natural way to parameterize the motion of point particles through space-time. Now at this stage you're feeling slightly ripped off because I wanted to give you a tensorial version of velocity and acceleration, and with this as preface we'll now tensorialize the idea of velocity and acceleration. Velocity and acceleration of what? Well, let's have some point particle evolving in space and time. It always moves through space-time. Even if it's stationary relative to you, it's going to grow old and trace out some straight line in space-time. So here we have a point particle in space-time. It's x mu. There's many of them. Infinitely many x mu's, infinitely many events as this point particle evolves through space and time, traces out a trajectory. That trajectory is naturally parameterized by the proper time, tau, the time attached to the wristwatch on this event. And this object is a tensor. Tau is a tensor. X mu is a tensor. We want to tensorialize velocity. Well, velocity is time rate of change of position. That's ordinary three-dimensional velocity, which is not a tensor. It can't be a tensor because if we're in space-time, tensor either has 0 index, in which case it has 1 value, or 1 index, in which case it can take 4 values, or 2 indices, 16 and so on. Ordinary velocity has 3 components, 3 values, 3 components is a better language, and can't be a tensor. It just doesn't have the right number of components. How do we tensorialize velocity? Well, let's forget about ordinary velocity for a second. I'm going to denote 4-dimensional velocity by, sorry, I lied before. I'll often call this, I'll call it both u and v, but let me call it u. For velocity, this tensorial version of velocity. Well, velocity is time rate of change of position, so let the tensor velocity, the for velocity, capital U, be the, instead of the time rate of change of position, let it be the proper time rate of change of position in space-time. Just to repeat, velocity is d by dt of position, for velocity is d by d tau of for position of this point particle, as it were, in space-time. For acceleration is either the proper time rate of change of the for velocity. Again, these are natural generalizations of the corresponding Newtonian results, or equivalently, the second proper time rate of change of the for position. And I could write that as I mean, here I'm flicking between the vector notation, which I could also write, by the way, as u superscript mu. This I could write, if I wanted to, as a boldface x. I'll use this very rarely, by the way. So 4 velocity, 4 acceleration. These are tensors, because we learned that when you restrict yourselves to linear coordinate transformations, such as the Lorentz transformations are, we learned that if your coordinate transformations are linear, then your p's are constant, and what? And the derivative of a tensor is a tensor, if. And so since we've got a tensor and we're differentiating it once or twice, the u and the a will be tensors. But how does the 4 velocity relate to the ordinary 3-dimensional velocity? So let's work it out. By definition, it's dx mu d tau. I'll leave off this explicit tau dependence. Now here's a trick I'm going to use often. When you're looking at this point particle evolving through space-time, you're rigidly attached to this S frame, and you've got your clock. Never mind the clock attached to the particle, which is ticking away as a tau. I want to do things, my mechanics, by looking at this point particle from the perspective of my frame, or your frame, inertial frame S, and your time t. And I don't like this tau. It might be a natural quantity with which to parameterize the motion, but ultimately I want to read the time on my clock, not their clock, right? So let's replace, via the chain rule, d by d tau with dt by d tau times d by dt. I've introduced my time. Now the equation's a bit ugly because it mixes times from 2 different frames, but that's all right. It's all right because dt by d tau, somewhat conveniently, is calculated here. dt d tau is the ratio of the two time intervals between tick and tock. Moving clocks run slow by a factor of gamma, so dt divided by d tau is gamma. So a trick that we use often is that dt divided by d tau is a gamma factor corresponding to the speed of the particle at a given instant of time t relative to this frame. So what we've just learned is a trick I'm going to use a few times today, so I'm going to underline it in red, that d by d tau is the same thing as gamma d by dt. Yep. So I'll use this a couple of times today. These things are the same thing. Good. What do I want to differentiate with respect to time? I want to differentiate x superscript mu. Let me write that component-wise. X naught, which is ct. Yep. Top board, bottom right. X naught, x1, x2, x3, x, y, z. And I want to differentiate that with respect to time. And that will give me u, the 4 velocity, what I want. Well, there's the gamma factor. If I differentiate ct with respect to t, I get c. In a sense, this is a velocity with which you grow old, yep, in space-time. d by dt of x, y, z is just going to give me the ordinary 3-dimensional velocity. And I'm denoting ordinary 3-dimensional vectors with lowercase letters and a vector symbol. So this is how the ordinary 3-dimensional velocity relate, which is a non-tensor, and gamma, which is also a non-tensor. Neither transform as tensors. You know, this transforms according to the Einstein velocity transformation formula, which is not the Lorentz transformations. And this object translates in a disgusting way, as you'll see from one of the appropriate exercises. So this is the 4 velocity, the tensorial version of velocity. And I could multiply the gamma through if I wanted to, and call this gamma c, gamma u. So this is how to tensorialize, in fact, 3 non-tensors, 3-dimensional velocity, gamma factor, so 2 non-tensors, 3 velocity and gamma factor, stuff them into this, and you'll get a tensor, the so-called 4 velocity. I want to use similar logic to work out the 4 acceleration, which is going to be d by d tau of u. Same trick in red. I'm going to replace d by d tau with gamma d by dt. Gamma d by dt. What am I differentiating with respect to time? Gamma c, gamma u. And I'll drop the u dependence here, gamma c, gamma u. But be careful, right? Be careful. The speed is going to depend on time. We're in frame S. Particles moving, it's going to be accelerating in general. The speed and hence the gamma factor will depend on time. The velocities will depend on time. So when I differentiate with respect to time here, yep, I've got the gamma out the front. Again, I'll drop the explicit functional dependence. And let me denote d by dt with a dot, an over dot. D by dt of gamma c will be gamma dot c. C is independent of time. Here, both gamma and u are a function of time. So when I differentiate, I'm going to need the product rule. Differentiate the first object, leaving the second alone, and then leave the first object alone and differentiate the second. And du dt will be the three-dimensional acceleration a. So this is the formula that we want for acceleration. It's a little bit more complicated than we might have expected, but there you go. A is not a tensor, gamma is not a tensor, u is not a tensor, gamma dot is not a tensor, but stuff these four non-tensor quantities into this expression, and you will get an object, the 4 acceleration, which transforms as a tensor and therefore is a tensor. By the way, if you were to go to the instantaneous rest frame of the particle is moving around, but you could imagine at some instant of time that you're in a frame of reference that's relative to you, which is moving instantaneously with the velocity of the particle. Yep. So here's a particle doing its thing, accelerating, but at some instant of your time, s time, that particle is moving with velocity v relative to you. You erect inertial frame, which at that precise instant of your time is moving at this precise velocity v, and at that instant of your time, this particle will be instantaneously at rest. In that frame, this has a special name, the instantaneous co-moving local inertial reference frame, just to repeat, the instantaneous co-moving local inertial reference frame. In that frame, instantaneous co-moving local inertial reference frame, the Ikmalov, yep. This 4 velocity. Now you need to be careful here. In that frame, u is naught, yep, by construction. In that frame, gamma is 1, yep, but it's not obvious that gamma dot is 1, right? Gamma might be 1, but gamma dot is actually 0. You need to think about why. The point is that the gammas become 1s, that's obvious. The gamma dots become 0, slightly less obvious. U is naught, and you're just left with the 4 velocity being naught, comma, a in the instantaneous co-moving local inertial reference frame. And what we see is that this 4 acceleration a is 0 if and only if the magnitude of the 3 acceleration in the rest frame vanishes. Now I want to look into, close this section by looking at the absolute significance of certain scalar products of two 4 vectors, two 4 velocities. Remember that when you have the dot product of two 4 vectors, that this is not a Euclidean space, so let me be explicit. The 3 components of the velocity of some 4 vector u, some object that transforms as a vector. Similarly for the 4 components of the vector v, and I'll remind you that the dot product is u0, v0, and then the all-important minus signs, u1, v1 minus, u2, v2 minus, u3, v3. So the all-important minus signs, which I can't emphasize enough. This is not a Euclidean space. This is a pseudo-Euclidean space. Yep. So suppose that I was to have 2 particles hooning through space-time, and those 2 particles will have respective 4 velocities u and v. Now, u is a rank 1 tensor, v is a rank 1 tensor. The dot product, on the other hand, is a rank 0 tensor. So it's an object upon which all inertial observers will agree, and here's the point. since every inertial observer agrees on this dot product, A, it has a geometric significance, and B, you can calculate it in any reference frame. You can calculate this object in any reference frame, so why not calculate it in a reference frame in which your mathematics is easier? Yep. So as an example, let's go to the rest frame of the second particle. So we're going to go to a frame of reference in which this object is at rest, as always, relative to some inertial frame S. So here's our frame S, and I'm going to choose that frame S to be such that this particle is instantaneously at rest. Because this is an absolute, I can calculate it in any frame. Let's choose a frame in which V is at rest. Now, for velocity of material particles is this object, gamma C, gamma U. So gamma C, gamma U. Yep. So we want to write down the components of U and V. Gamma C, gamma U. Well, this thing's instantaneously at rest, so gamma is 1. Gamma C is C, and gamma U is 0. Now I could write 0, 0, 0, but let me write a three-dimensional vector 0. So this is the full velocity of particle V in this frame S, in which the second particle V is instantaneously at rest. First particle, gamma C, gamma U. So this velocity U and the corresponding speed U are all relative to the frame S. So when I do the dot product, when I do the dot product, you take the temporal components and you multiply them together, which will be gamma of U C squared, gamma of U C squared. Then you subtract the dot product. You subtract the dot product of the spatial parts, minus U1 V1, minus U2 V2, minus U3 V3. So you're going to subtract gamma U vector dotted with 0, which is 0. So this is the dot product of the full velocity of the two vectors. It has an absolute significance because it's a rank 0 tensor, and that absolute significance is it equals a gamma factor considered as a function of U. And by construction, since I made one of these particles at rest, U will be the relative speed of the two particles. And the relative speed, the speed between the two particles relative to an inertial frame which is locally at rest with respect to either particle it's a frame-independent quantity because there's only two frames you can calculate it in, rest frame of particle A or rest frame of particle B, and they'll both give you the same value. So here we have our dot product of the four vectors, four velocities of two material particles having an absolute significance. This will be useful to us in studying relativistic mechanics. In fact, let's move on to relativistic mechanics now. This is chapter 7, relativistic mechanics. So relativistic mechanics 1. So the remainder of the course has 3 chapters. Chapter 7, which is relativistic mechanics 1. Chapter 8, which is relativistic mechanics 2. We'll then move on to classical relativistic fields in the final chapter, chapter 9. Now what we want to do here, just by way of introduction, by way of a brief intro, is just to revisit Newtonian mechanics. Now, we already made some modifications to make this relativistic, but I want to revisit this from a tensorial perspective. I also want to push it much further than we did previously. But in order to do that, we need to introduce one hypothesis, which is the conservation of form momentum. And form momentum, which I've yet to introduce, form momentum, denoted by capital P, is the four-dimensional version of the tensor version of momentum. It's also called the energy momentum tensor. And so the key point here is that most of this course to date has been derived via logical deductions based on Einstein's axioms. I want to introduce the only additional assumption in this course, which is going to be the conservation of form momentum. And I know that I've yet to define what form momentum is, but before I do so, let me define its conservation. Now, a classic technique when considering collisions, classical or quantum collision problems, is you have a series of particles before the collision, which are free and well separated, and travelling, in a sense, without forces acting on them because they're so far apart. They then come together into some complicated interaction region, and then weird things can happen, chaotic dynamics, all sorts of processes. And I don't care what's going to happen in this complicated region where these particles meet and interact, because in the context of a collision problem, after the collision, these particles will emerge. Now the number and the nature of the particles may change. I may have 3 particles going in and 2 particles going out. I may have an electron-positron pair coming in and several photons coming out. The number and the nature of the particles may change, but they start off as a certain number of free particles. They end up as a certain number of free particles, and the key point here is, if I want to avoid needing to deal with all the complicated stuff that goes on in the collision region, then what I can do is apply certain conservation laws. I demand that energy be conserved. I demand that momentum be conserved. I demand that angular momentum be conserved. I demand that electric charge be conserved. Whatever conservation laws I can kick in might allow me to calculate, without knowing what happens in the complicated region here. I know that certain things are conserved, and that will let me calculate the final states of the particles well after the collision by using conservation laws, classic technique. Conservation of form momentum, I've yet to define what form momentum is, but let me denote by P ins, the form momenta. And this superscript, by the way, is not a tensor index, it's just a label. So I'm going to label the incoming form momenta by P1 in, P2 in, etc. And similarly for the outgoing form momenta, P1 out, etc. Yep. And I'm going to ascribe and write down a formula for the form momentum of each material particle. But the hypothesis, and this is the additional hypothesis of conservation of form momenta, is that if we sum over the incoming form momenta of the particles, that's going to equal the sum over the outgoing form momenta of the particles. This additional hypothesis is the hypothesis of conservation of form momentum for this form momentum that I've yet to define. Now, this law has to have a few things. Number one, it's got to reduce to the corresponding non-relativistic limit. Yep. So it's got to have the correct NRL, not National Rugby League, but non-relativistic limit. Number B, it's got to be number B. It's got to be consistent with the axioms of special relativity. It's got to respect the axioms of special relativity. And third, it's got to give the correct results, right? In the sense of this hypothesis, I might say it's natural, but if it disagrees with the experiment, then my theory goes out the door. The point is that I need the results of this hypothesis to be consistent with the results of experiment. So with all that, and with the promise that I'll come back to this list, I'm going to define form momentum. Now, momentum is mass times velocity. Momentum is not a tensor, mass is not a tensor, and velocity is not a tensor. But rest mass is a tensor, and fall velocity is a tensor. So it's natural, instead of having momentum being mass times velocity, I'm instead going to say that form momentum is rest mass times fall velocity. This is a tensor, a rank 0 tensor. This is a tensor, a rank 1 tensor. The product of tensors is a tensor, hence P is a tensor. So this is form momentum. Now, we learned a couple of blackboards ago that for velocity is gamma c gamma u. It's a gamma factor as a function of the speed of the particle times this object with 4 components, temporal and spatial components. We could unite these two things into the mass of the particle. Rest mass times the gamma factor is the moving mass, m, or I could call it m of u if I wanted to. C u. I could leave it like this. I could bring the m inside. Let me drop this, the dependence. MC, m, u. So this is the form that I'll talk about a lot now. So let's put a star next to it. Having said that, another form of this, form momentum, if I multiply this by c and divide by c, I'll get mc squared on C, I'll get mc squared on C, which is nothing more than E on C. And u is the momentum, the 3 momentum. So this is the second form of the equation. And let me replace this mu with the ordinary 3 momentum p. Again, I emphasise that this 4 momentum is a tensor. Now, I'm still not happy because I've got this list of things that my hypothesis of 4 momentum conservation must lead to. I've got my eye on this list. Now, since 4 momentum has 2 bits, the conservation law here must have 2 bits, right? So the sum of the incoming 4 momentum equals the sum of the outgoing 4 momenta, sorry. So therefore the sum of the ingoing MCs, yep. So incoming M's, and the C is just going to cancel, right? So this is nothing more than conservation of mass. Sum of the incoming masses equals sum of the outgoing masses, yep. And similarly, conservation of 4 momentum has this bit, which is the sum of the incoming momenta, the ordinary 3 Newtonian momenta, equals the sum of the outgoing. Now, superficially, this looks like Newton, right? Superficially, it looks like Newton, and does reduce to Newton in the corresponding limit. But remember, conservation of mass, Newton would say, of course, mass is conserved. But remember that these are moving masses, yep. In relativity, these are rest masses times the gamma factors. But in the non-relativistic limit, the gamma factors are 1. This is conservation of mass. This is conservation of, let me call it 3 momentum, both of which are explicit in Newtonian mechanics, although Newton would regard this one as kind of obvious. This one is profound. But remember that this is moving mass, and this is moving mass times velocity. But with that relativistic twist, the hypothesis of conservation of 4 momentum is the conservation of mass and the conservation of 3 momentum. I mentioned earlier that this so-called 4 momentum is also called the energy momentum tensor. It's called the energy momentum tensor because it tensorializes energy and momentum. Yep. So it's also called the energy momentum tensor. By the way, this is the more common form in which this equation is written. That's it for this section. 25, some 4 momentum identities. Now, I'm not just calculating these for the hell of it. These 4 momentum identities, I'm calculating them because I need to use them soon enough. So the first is the energy momentum mass relationship. You remember that. It's E squared equals P squared, C squared, etc. This relates the energy E, momentum P, and rest mass m naught of a point particle. Now let me derive this in 2 lines. Yep. Energy momentum tensor, P squared, is a dot product of this with itself. That's going to be an absolute. It's going to have the same value in every frame of reference. In a particular frame of reference, the object will have a particular moving mass m and a particular momentum p. Fair enough. If I square this with itself, I've got, some frame of reference, inertial frame. And when I square it, remember that means this multiplied by itself minus this dotted with itself, that all-important minus sign. But this is an absolute. This has the same value in every reference frame. If I was in a frame of reference in which this object was at rest, this m would become the rest mass, and this p would become 0. This object is the same in every frame. I can calculate it in any frame I want. I've calculated it in one frame. If I now calculate it in the rest frame, I'll get exactly the same result. And in the rest frame, I'll have this squared minus this dotted with itself, which is naught. So we now have this expression here. If I multiply through by c squared, I'll get m squared c to the fourth, which is nothing more than e squared. Pull this to the right-hand side, multiply by c squared, multiply by c squared, and there's your energy momentum mass relationship. It's nothing more really than an expression that p squared is an absolute. But compare the swiftness of that derivation with the ugly derivation that I gave in the first class. This is also a nice example of the fact that tensor analysis, once you start using it, is often leads to very, very simple and swift calculations. Let's consider two material particles with respective form momenta, capital P1 and capital P2. And I want to ask the question, the form momentum of particle 1, this is a bold P, will be mcp, yep. And in some frame of reference, the mass would be, I don't know, m1 as a function of the velocity v1 of that particle, c, and then the momentum of that particle number 1. I'm using a natural notation here. Similarly for P2, mass of particle 2 as a function of its speed, v2, c, P2. But again, the dot product of two full vectors is an absolute. It's something upon which all inertial observers agree. Yep. So we could calculate it in any frame of reference. So let's calculate it, for example, in the frame of reference in which the first particle is at rest. Remember, we multiply these things together, then we subtract the dot product of these. So if we're in the frame of rest of the first particle, I would have the product of these. I'm going to get a c squared. The mass, however, becomes the rest mass of particle 1, which I'll call m01. There's a c squared. We have m2 as a function of v2, and here v is going to be the relative speed of the particles. I'll call it v. Minus p1 dot p2, but one of them vanishes. There we go. So this is the dot product of the two form momenta. But the mass of particle 2, the moving mass, as considered as a function of the speed, will be its rest mass m2 times the gamma factor times of its relative speed times c squared. So this is the dot product of the two form momenta of the particle. It's a product of the rest masses times the gamma factor considered as a function of the relative speed times c squared. A third of three identities I need is called the elastic collision lemma. So let's consider some process in which we have an incoming form momentum, or two incoming form momenta P and Q, some collision, and then outgoing form momenta P prime and Q prime. And these are form momenta of particles. Now, if you conserve form momentum, you'll have the following. If you dot product this with itself, you'll get p squared plus 2, and these again, four-dimensional dot products. Yep. You'll get the following. P prime squared, Q prime squared, cross term. But we saw that the square of the form momentum of a material particle has an absolute significance. It's a rest mass squared times c squared. Now we're going to define an elastic collision in a fairly bizarre way, not in the way that you're used to. We're going to define an elastic collision as a collision in which the rest masses are preserved. So the rest mass of P and the rest mass of P prime has to be the same. The rest mass of Q and the rest mass of Q prime has to be the same. Yep. I don't care if it's an electron turning into a positron. The point is rest masses are preserved. And the square of the form momentum is, as I said, proportional to the square of the rest mass. If rest masses are preserved, then P squared equals P prime squared, Q squared equals Q prime squared. I cancel the 2's. and I get what's called the elastic collision lemma, which is that P dotted with Q before the collision. Again, it's algebraically trivial, but we're doing something very interesting and profound. We're invoking conservation laws to let us avoid the details of the collision process, and using this kind of thing will allow us to calculate some interesting and excellent stuff, on which point I'll stop. Thank you.